What's up everybody? Now in the part 3 of our MPC playlist, right? And now we are looking at this nonlinear two-dimensional, I mean the plant having two states. This problem, we only have one D input signal, right? That we have control over to drive the states to 0, right? Again, I mean we are considering regularization problem, right? And regulation problem, right? Okay, and first things first, just let us discretize the plant here. This is what we have, right, using forward error approximation. Okay, and again by arranging the terms, this is what we have. And let me change colors. And okay, again, like we did in the previous example, this is the nonlinear term, right? And we know how to linearize that using Taylor approximation, right? In the vicinity of the given, maybe let's call it operating point or linearization point. Okay, and that is it, right? And we know it because of the previous video, right? And all right, let's directly put this expression, right? And let's check the MATLAB code. Okay, in the meantime, you try to maybe just pause the video and try to look at this expression, because this is the expression that we are going to employ in our optimization codes. Okay, let's change the screen. All right, I think you are able to see that, and I am not going to run it because it kind of takes considerable amount of time, and I don't want to waste your time. All right, let's clear the memory here. This is our problem, right? This is our continuous time problem, and we just discretize that, right? Okay, and again just arbitrarily picking, and n equals like 500 step size, right? This is our like time steps. Okay, and this is our sampling period, t equals 0.01 seconds, right? And okay, again input trajectory and state trajectories we are just defining, initiating using stp command. And again x bar, and notice this is two rows. I mean this is a matrix. Since we have x1 and x2, since we have two states, right, we are just making this as two rows, having two rows and n columns, right, instead of compared to the case where we use like one row and n columns, because we only had one state vector to deal with, state variable to deal with, right? Okay, and okay, I just again written this Taylor approximation related expressions to remind ourselves about the linearization process, right? And here this is for x1 dot dynamics, right? And we just change this, what was that term, x2 square, right? Here we can see x2 of k square term, we just changed it with this expression. Okay, all right. And all right, maybe I should do something like this. Yeah, this is the expression. We just changed it using Taylor approximation. All right, and these two, and second constraint is comes from this x2 dot dynamics. All right, and here we can see our input entering to the system, and we are also employing that type of rate limit conditions, right? We are limiting our change of our u dot expression. Okay, again initial conditions 10, 5, right? x1 of 0 equals 10 and x2 of 0 equals 5. We are considering these initial conditions, right? And we are imposing how to constraints and we want our states to, since this is a regression problem, right, we want our states to converge to 0, right? Okay, and for the final input signal, right, we are just imposing that 0, u of n, capital N equals 0 constraint. I don't think it's 100% necessary, but yeah, for some reason I did that, right? And I'm looking at my screen, and yeah, this is the okay. So this is a long line, and you are able to see that. So right, this is there is nothing more on this line. Okay, all right. So don't worry about it. And okay, and again, some type of saturation constraints, and also since we have some inside information about our system, we are also imposing that constraint, because we know that inherently for our problem the states will not take any values outside of this box limits, right? Okay, interval, and right, again the same thing that we did, and STP settings, I'm using mosaic, right? And again try to minimize this objective function, which is summing over this quadratic constraint, right? This is like something that we are used to now. Okay, and optimize that and get the x bar, right? And iteratively solve that, because this is a nonlinear optimization problem, and we are employing alternation methods to solve that problem, right? And this is, we are out of the, I guess, land of convex optimization problems, right? So right, this is uncharted waters, we are here. I'm not going to make the mistake of running this code, because it takes considerable amount of time, right? Okay, and just I am going to run this. I'm going to plot the results rather. Let me plot them. Okay, here, and let me make it bigger. Okay, make it bigger. All right, and red line indicates x1 trajectory, and we know that x1 starts from 10 and x2 starts from 5, right? Here we can see that. And black line indicates x2 trajectories, okay, trajectory. And and now we are looking at u, like input trajectory. So this is the input signal that we need to employ or apply to our system to drive the states to 0, right? Okay, and I'm looking at the problem and thinking about if there's something that I need to discuss more. Yeah, maybe we could, for example, lower the lower limit of u dots, right? Maybe I can make this 5 or something, right, rather than being 10. And of course there are things that you can change depending on the problem, depending on your constraints, right? Okay, for example, maybe you don't have the capability of employing negative input signals. I'm just for sake of giving an example, and yeah, you can impose that type of hard constraints on your problem when constructing your optimization problem. Okay, and again, if you look at this is like more than 30 lines, but approximately 30 lines of code, right? Here you can see. So yeah, that's it, and this is MPC. All right, that's it, and thanks for watching.